Hello everyone. In this lecture, we will discuss a new group, and this group is formed using the set of integers reduced under the modulo n system. So, if we have the set of integers z with elements 0 plus minus 1 plus minus 2 plus minus 3 and so on, then if we reduce this set under modulo n system, then this set is denoted as Zn, and it will have the elements 0, 1, 2, 3, 4, 5 and so on up to n minus 1. So if we remove this 0 element from the set of integers, then we will not get 0 over here, and we put a condition that n must be prime. If we take n as prime, then this set, when we have removed the 0 and n is taken as prime, then it can be written as Zp asterisk. Here asterisk represents that it doesn't have the 0 element, and p represents that n must be prime. So it will have the elements 1, 2, 3 up to p minus 1. Now we define an operation of multiplication modulo n over this set. Multiplication modulo p, since we have taken n as prime, then it is written as p. So we are defining the operation of multiplication modulo p as when a and b are multiplied under the modulo p system, then it will yield the element remainder obtained when a into b is divided by p. Basically, this multiplication modulo p represents that the remainder obtained when a into b is divided by p. Suppose we are multiplying 5 and 7 under modulo 5 system. If we are multiplying, suppose we have taken it as 3. If we are multiplying 3 and 7 under the modulo p must be prime, so we have taken p as 5. So if we are multiplying 3 and 7 under multiplication modulo 5, then we will have 21 reduced under mod 5, and it means we must divide 21 by 50, and we are getting 1 as remainder, therefore its answer will be 1. Or in this sense, we can see that when 3 and 7 are multiplied and divided by 5, then the remainder obtained. So we have multiplied 3 and 7, it is obtained as 21, and we reduced it using modulo 5. So in under modulo 5, what will happen? We will divide 21 by mod 5, and the remainder which will be obtained will be the answer. So 3 into 7 under modulo 5 will become 1. So we have defined an operation of multiplication modulo p, and under this operation, this set Zp asterisk under this operation of multiplication modulo p forms a group. Basically it forms an abelian group, and we denote it as Zp asterisk under multiplication modulo p, and it is an abelian group. Now to clear our understanding, we will take a particular example of this group. Suppose we take p as 7. If we take p as 7, then we get Z7 asterisk as 1, 2, 3, 1, 2, 3 up to p minus 1. So we will have 1, 2, 3 up to 4, 5 and up to 6. This will be the set Z7 asterisk, and we will define an operation of multiplication modulo 7 over this set. Now this set Z7 asterisk under this operation of multiplication modulo 7 will form a group. We can observe it using the composition table or Cayley table. So here we are forming the Cayley table 1, 2, 3, 4, 5, 6 written in the top row and in the first vertical line. Now if we multiply these elements under multiplication modulo 7, then we can observe that 1 into 1, 1, which is less than 7, therefore it will remain 1. 1 into 2, 2, 1 into 3, 3, 1 into 4, 4, 1 into 5, 5, 1 into 6, 6. These elements will remain as it is. We will not need to divide these elements by 7, since 7 is a greater element and these elements are less than 7. Now if we multiply 2 by 1, then we will get 2, 2 by 2, 4, 2 by 3, 6. Now if we multiply 2 by 4, then we will get 8, and 8 under modulo 7 system will become 1. So here we will write 1. 2 5s are 10. Under modulo 7, the remainder will become 3. 2 6 are 12. 2 under multiplication modulo 7 6. 12 reduced under mod 7, then it will become 5. Now 3 multiplied by 1 3. 3 multiplied by 2 6. 3 3s are 9. Under 7 2. 3 4s are 12. Under mod 7 5. 3 5s are 15. Under mod 7 1. 3 6 are 18. Under mod 7 4. Similarly, when 4 is multiplied by 1, we will get 4, which is less than 7, written as it is. 4 multiplied by 2, then we will get 8, and under modulo 7 system it will become 1. 4 multiplied by 3, we will get 12, and under modulo 7 system it will become 5. 4 multiplied by 4, we will get 16. 16 on division by 7 will yield the remainder 2. Similarly, 4 multiplied by 5 will yield the remainder 6, and 4 multiplied by 6 will yield the remainder 3 under mod 7 system. Now 5 into 1 5, 5 into 10, 5 into 2 10, which will become 3, 5 into 3 15, which will become 1, 5 into 4 20, which will become 6, 5 into 5 25, which will become 4, 5 into 6 30, which will become 2. Now 6 into 1 6, 6 into 2 12, under mod 7 it will become 5, 6 into 3 18, under mod 7 it will become 4, 6 into 4 24, under mod 7 it will become 3, 6 into 5 30, under mod 7 it will become 2, 6 into 6 36, under mod 7 system it will become 1. So we have prepared a composition table for this group. Now we can easily observe that the first axiom, closure axiom, is satisfied since all the elements of the composition table belongs to the set itself. No element is from outside this set. Therefore, we can say that the closure axiom is satisfied. The second axiom is associative axiom. The second axiom is associative axiom, and we know that in general multiplication of integers is associative. So these are integers reduced under modulo n system. So these will remain the integers. So multiplication of integers is associative, therefore associative axiom will remain satisfied. In general, it will satisfy for integers. Now the third axiom is existence of identity. From the composition table, we can easily observe that the first row is similar to the top row. The first row and the top row are similar. Therefore, the element corresponding to first row will be the identity element. So here the element corresponding to the first row is 1. Therefore, 1 is the identity element. Thus, the identity element exists in this set. Now, the next axiom is existence of inverse. To check the inverse of the elements, we must know what the identity of the set is. Here the identity is 1, therefore the inverse can be easily identified by marking 1 in the composition table and observing the elements corresponding to the left and the top. Here for this one we have 1 on the left and 1 on the top. It means 1 and 1 are the inverses of each other, therefore 1 is self inverse. Similarly, for this one we have 2 and 4, therefore the inverse of 2 is 4 and the inverse of 4 is 2. Similarly, we can say see 3 corresponding to 3, we have 1 over here and here it is 5. Thus the inverse of 3 is 5 and the inverse of 5 is 3. Similarly, we can observe that the inverse of 4 is 2 and the inverse of 2 is 4. Here 5 3, the inverse of 5 is 3. 1 is over here, therefore the inverse of 6 is 6. 6 and 1 are self inverse, and the inverse of 2 is 4 and the inverse of 4 is 2. The inverse of 3 is 5 and the inverse of 5 is 3. Therefore the inverse of all the elements, we can see that the inverse of all the elements of the set exist in this set. Therefore all the axioms are satisfied over here, and hence we can conclude that this set Z7 asterisk with respect to the multiplication modulo 7 forms a group. Now if we see the commutative axiom, then we can easily see that if we multiply two numbers under modulo 7 system and we change their order, suppose we have a under multiplication modulo 7b or b under multiplication modulo 7a, we have reversed their orders under multiplication. When we have reversed their orders, then the result will remain same. You can easily observe that. Now since commutative, therefore the commutative axiom will be satisfied, and since commutative axiom is satisfied, therefore the group will be commutative or abelian. Hence we can conclude that Z7 asterisk under multiplication modulo 7 forms an abelian group. So in general, Zn when n is prime, removing 0 forms a group under the multiplication modulo n, but n must be prime. Thanks for watching.